All right, welcome to the last lesson of Unit 4. We are looking at infinite geometric series. So the difference between last lesson and this lesson is, well, we are dealing with infinite series. Okay, so what is that? Well, basically, geometric series, recall it was the sum of a geometric sequence. So infinite geometric series will be the sum of n infinite. Okay, I can't spell infinite. Infinite geometric sequence. So we're going to keep adding forever. Geometric sequence. Okay, we're going to keep adding until we're just going to keep adding. Okay, partial. So that's the sum of infinite geometric sequence. That's infinite geometric series. Partial sum is the sum of few terms. Okay, not all of them, but let's say first 5 terms, the first 10 terms. Okay, so partial, so it's just only part of it, right? Sum of a part of a sequence. That's what a partial sum is. Okay. Okay. So again, just some definitions. Okay. So here it says if the sequence of a partial sums converges to a constant value, then the geometric series is convergent. Okay, we talk about this. It approaches to a value, but last time we were talking about if the sequence was a converging sequence. This is a convergent series. So if we are adding and it gets closer and closer to a value when we keep adding, and then we call that a convergent series. Okay, and the constant value is the finite sum of the series. Okay, so sum to infinity, it just means that we keep adding forever. It's kind of like that, sum to infinity. Okay, you just keep adding, and we use sum to infinity as infinity. Okay, that is the sum to infinity, and there is a formula for this. It is right here. Okay, sum to infinity, it's t1 over 1 minus r. We'll look into that in a second. Okay, again, sum to infinity just means that you keep adding forever. Okay, so let's look at convergent series here. Here are 3 series. We want to predict which or whether each infinite geometric series has a finite sum. So if we keep adding these numbers, are we going to end up with a value that is, are we going to get a sum that is close to a value and it won't really change much? So in this case, I mean, you can try to put it into calculator. You can see the numbers are getting smaller and smaller. I know one of them is adding and one of them subtracting, but then again, the numbers that we're adding or subtracting is getting smaller and smaller. So we probably will get a finite sum. Okay, we'll get a finite sum. This one will get a finite sum because again, the numbers are getting smaller and smaller. So when we add, you're adding like closer and closer to 0, which means you're not really adding anything to it if you're adding almost 0. Part B, this is not going to be a finite sum. No, because again, that's 0.2, that's 0.4, 0.8, 1.6, and it's going to be 3.2, 6.4. You're adding bigger and bigger numbers. So you're not going to, so the sum is not going to approach to a particular value. Okay, so this is not going to be a finite sum. This is going to be a larger number. It's going to be infinity basically because you're just keeping adding up bigger numbers. Okay, finally, for part C, this one is going to get a finite sum. And again, because the common ratio is actually 1/2 here, this common ratio is 2, this common ratio is negative 1/2. When you add numbers that's smaller, and actually there's a common ratio to it, it's getting smaller and smaller at a rate. At the end of the day, you're going to add like a 0 to it. So you're not really adding anything to it. So you are going to end up with a finite sum, which means, again, the sum is going to approach to a particular value. Okay, so it says here, for most geometric series, the sum keeps getting either larger or smaller as n increases. Except when you're adding numbers that's close to 0. Okay, really close to 0. It says under what conditions will the sum approach a specific number, or under what condition will the sum converge? Again, I just show you, as long as the ratio is between -1 and 1. So it says when the common ratio is between -1 and 1, we will get a finite sum. If the common ratio is is bigger than 1 or less than -1, then we will not. Then we will not get a finite sum. Okay. In fact, it's gonna approach infinity or negative infinity, right? As you add bigger and bigger numbers or more and more negative numbers. Okay. Yeah. So that's that. Let's see here. We see how do we get this formula. Okay, so here is the sum to infinity formula. Notice how this is actually quite close to Sn formula, the sum of n terms. This is 1 minus r to the power of n, 1 minus r. So notice this portion disappeared, okay? We just have t1 over 1 minus r. So this really has the concept of limit to this. Think about what happened if r is small, right? 0.5, let's say. And n is a large number. So if you think about, let's say 0.5 to the power of 2, sure, that's not too bad, 0.25. But if you go like 0.5 to the power of 100, if you put this into calculator, I don't even know, you know what, I'm going to try to see what happens. Okay, it's a very, very small number. It says 7.9 times 10 to the negative 31. So it's going to be 0.00031 zeros and then 7, or 30 zeros and then 7, 9. So it's a very, very tiny number. So you're really not adding anything to it, okay? And this is basically nothing. So this really doesn't matter because this portion is going to be 0. And 1 minus 0 is still just 1. And therefore, you don't need that anymore. And that's why you get this formula when n is large, right? When n is all very, very big number, this 1 minus r to the power of n is like 0. Given that r is between -1 and 1, right? So this is important, okay? It says r cannot equal to 1 and r has to be between -1 and 1. Okay, so these two are that's the condition. Okay, be careful. R has to be between -1 and 1 in order for you to use this formula. If r, the common ratio, is bigger than 1 or less than -1, then you cannot use this formula. Okay, because then this won't equal to 0. Okay, so be careful. All right, let's look at some examples here. It says find the sum of each geometric series. So what we need to do first is to figure out the common ratio. And again, that is second term divided by the first. That's 1/2, which meets this requirement. So then we can use the formula sum to infinity, which is equal to t1 over 1 minus r. t1 is simply the first term. 1 minus the common ratio is 1/2. This is 16 divided by 1/2, which is going to be 32. So if you keep adding with this sequence, you will not get, I mean, the sum is going to be really close to 32, and we just say that's 32. Okay, it will actually never be 32, but you'll be really close. Okay, and again, that has the concept of limit, which you will learn in calculus. Okay, anyways, so here's the second example, part B. So again, if we want to rewrite this properly, again, or doesn't show it this way, I don't know why. Okay, but anyways, this is how it should be written. What we need to do is to figure out t1 first, because we'll write first few terms and then see if the common ratio is definitely between -1 and 1. I think it's going to be, because that should be the ratio, but we know what we'll see. The first term will be 1/2 -1 over 3 to the power of k. Again, k starts with 0, so there's 0, that's the first term. Anything power of 0 is 1, so this is simply 1/2. The second term is going to be 1/2 times -1 over 3 to the power of 1. That's going to be -1 over 6. Or we'll do one more, -1 squared. This is going to be 1 over 18. So you can see the common ratio is simply the second term divided by the first term. This is going to be -1 over 3. Okay, recall this is -1 over 6 divided by 1/2. And how you divide fraction is you multiply the reciprocal of the second fraction. And that's how you get -1 over 3. So now you have the common ratio, and we also have our first term. So we can actually find the sum. This is going to be t1, 1/2, divided by 1 minus the common ratio of -1 over 3. This is going to be 1 over 2 divided by, that's minus, so it's a plus. 1 plus 1/3 is 4/3. This is going to be 1 over 2. Again, divide fraction means multiply the reciprocal, so this is going to be times 3 over 4. 3 over 8 would be the answer, okay? When you keep adding, the number is going to, or the sum is going to get really, really close to that, okay? And we will say that that's the sum. Okay, hopefully this wasn't too difficult for you. Again, this formula is a lot simpler, actually, but you just need to figure out whether the common ratio is between -1 and 1, okay? That's the key, okay? The ratio has to be between -1 and 1. Okay, so let's see here. This is a different example here. It says write repeating decimal as a fraction. So we know a lot of times a fraction, if you change it to a decimal, it's actually just a repeating decimal. For example, 103, this is 0.3 repeating, right? So now we're going to go backwards. What if we're given this repeating decimals? How do you change this back to a fraction? Okay, so this is what we can do, okay? The 0.181818181818 can, and so on, can actually be written as a geometric series, okay? We can do it this way. We can say this is 0.18 times 10 to the power 0 plus 0.18, or you know what, never mind, I'm going to do it this way. This is 0.18 plus 0.0018 plus 0.000018 plus, I think you get where I'm going, right? 0.000018. So this one, these two 18 belongs here, these two 18 goes here, these two goes here, and these two goes there, and so on. Now, this is an infinite geometric series, right? Because this keeps on going forever. Now, this would have a finite sum because the common ratio, well, we can find that out, is 0.0018 divided by 0.18, right? Second term divided by the first term. This is actually 0.01. So now our common ratio is between -1 and 1, and this is an infinite geometric series, so we can use the sum to infinity formula. T1 is simply 0.18, and this is going to be 1 minus 0.01. Now, the problem is, if we work with decimals, I mean, you'll end up with decimal, right? So then we can't really write as a fraction. So what you need to do is you need to change this to fractions. 0.18 is same thing as 18 over 100. Okay, that's why it's 0.18, because it's 18 out of 100. 1 minus 0.01 is 0.99, which is 99 over 100. Okay, so now again, these are just divisional fractions, so now we multiply the reciprocal. They cancel out. You can divide both 18 and 99 by 9, so that's 9. 18 divided by 9 is 2, that's 11. So 2 out of 11 is actually 0.18181818, and so on. If you don't believe me, you can absolutely put this 2 out of 11 into your calculator, and you'll see you'll get 0.18 repeating. Okay, so that's kind of cool. We can actually turn a repeated decimal to a fraction. That's kind of neat. Okay, last example of this unit here. Let's see. It says a pile driver pounds a metal post into the ground. With the first impact, the post moves 30 centimeter. With the second impact, it moves 27 centimeter. Predict the total distance the post will be driven into the ground if, part A says, if the distance formed an arithmetic sequence and the post is pounded 8 times. So it says this is arithmetic sequence. So first one, it moves 30, and then moves 27, and then I guess the next one will be 24, and so on, right? So this can be written as a geometric sequence. Okay, sorry for interruption. Anyways, someone came in the room, so okay, that's where am I here? Okay, so yeah, this is an arithmetic sequence, so we can actually add them using arithmetic series formula, which was Sn is equal to what is it? T1 plus, oh shoot, I forgot the formula for arithmetic series. What is it again? Sn is equal to okay, so that was embarrassing. The formula for Sn was n times T1 plus Tn divided by 2, if you recall from math 10, okay? So I'll be honest with you, you probably won't see this question on the test. That's okay. I'll show you anyways, because this is arithmetic sequence or arithmetic series. Now, the problem is we don't know what T8 is, right? Because if you want to find sum of 8 terms, it'll be 8 times T1, which we know is 30, 30 plus Tn, which we don't know, divided by 2. But we can find Tn easily by using the Tn formula. I do remember Tn formula. That was T1 plus D times n minus 1. Okay, D times n minus 1. So T1 is 30. Common difference is actually negative 3. N is 8 minus 1. So if you put this into a calculator, this is 9. So now we can put 9 in here. And then we can find the sum of 8 terms to be 8 times 39 divided by 2. So that's 4 times 39, which is 156 centimeter. Okay. So if you keep pounding 8 times, you'll be 156 centimeters under the ground. Okay. Part B says, so that's a meter and 56 or 1.56 meters. That's kind of deep. Okay, part B says if the distance from a geometric sequence instead and is pounded 8 times. Okay, so then in that case, it would be 30 plus 27. So you can see the common ratio is 27 over 30, which is 0.9, right? 90% of what it was. And I don't know what the next numbers are. Okay, that's fine. You need to actually use a calculator, to figure out. But we do know the formula for Sn. It was T1 times 1 minus the common ratio to the power of n over 1 minus r. We know the the T1, the first term is 30. 1 minus the common ratio, which is figured out, is 0.9. We wanted to do it 8 times. 1 minus r. Oh, we know the r is 0.9. Okay, so now we can put this into calculator. Let's see. 1 minus 0.9 to the power of 8 times 30 divided by 1 minus 0.9 is 0.1. So divided by 0.1, which is 170.86 meters. Oh, sorry, centimeters. Okay, so that would be the answer if it was a geometric sequence. Now you can think about whether you think it's geometric sequence or arithmetic sequence. Personally, I think this should be a geometric sequence in real life. That's just how I feel. Okay, I mean, you can feel differently. That's fine. It's your own opinion. I don't think there's a right answer or wrong answer unless we test it, right? Personally, I think it should be a geometric sequence. Anyways, last example here says the distance from a geometric sequence and the pose is pounded until it has essentially stopped moving. So we keep hitting it until it doesn't move anymore. Okay, so then what's the distance of that? So then I guess in that case, we're really looking for sum to infinity. Because it stopped moving, so the last one is almost 0, right? So that's what we're doing here, sum to infinity. We know T1 is, again, I'll write down the formula, 1 minus r. T1 is 30, 1 minus 0.9. So this is actually 300 centimeter if you put it into a calculator. Or it's 30 divided by 0.1, which is just 10 times as big, so 300 centimeters. Okay, so that would be the total distance that you can pound if this, if you continue to pound the metal. Okay, so that's it for this unit. Hopefully that's not too difficult for you. Yeah, we are finished.